Greetings, everybody, here and out in the Zoom world.
Are you sharing your screen?
Oh, I'm not yet. I did a test earlier and I was able to share my screen, so let me, I've unshared, you're not ready to figure it. Okay, screen sharing. So yeah, I'm Bruce Johnson. I'm next door at the ASRC, Advanced Science Research Center. Today we're going to talk about the software that we've developed over the last many years to count in its latest iteration. It started out as a program called NMR-VJ, that was visualization analysis. And we've added on to the front end of that full processing, so you can start with raw data. And we've added on to the far end structure calculation, chemical prediction, and ring NMR dynamics for doing dynamics analysis. So today we're going to walk you through. It's mostly going to be, some of it will be like hands on how to do stuff, and some of it will be just like, here's a feature. We're not going to have time in today's. And how long is the official till
2:30,
2:30?
whatever.
I've given like 4-day long, all day long workshops on this, so we're not going to do all that in an hour and a half. So part of it's just you can get a flavor of what's there, and then don't hesitate to contact us. Simon and Ellen are in the back of the room. Ellen's working on a lot of stuff. Simon's some of which I'll show you probably, and Simon's working on a lot of the ring dynamic stuff these days and this process and things like that. So if you try things and they don't work, don't give up. I'll come this right across the way. Okay, so I'm going to start out really basic. We'll get more complicated, but I'm going to start simple. I don't know how many people out there are actually doing NMR, but we're going to start pretty simple. Partly because then you'll sort of see step by step how to use the software, and we're gonna walk you through taking just a single FID, simulated and process that, and think about all the processing steps, and then we'll move on to more complicated experiments after that. So if you've gotten people out in the Zoom world there, don't hesitate to chime in if you're having troubles. It will be recorded, so that you can follow along later if you want to try things, not doing it hands-on. NMR effects and ring are definitely moving targets, so we're adding lots of stuff, and every time we add 3 new things, we break one existing thing. So doing these workshops is always a little bit of a what's currently working and what did we break. So there are a few things that I noted last night and this morning that were issues that we added recently. So that's why there will be a new version in the next few days, probably. Okay, so if you start up NMRFX, and as you may have learned, it will run on your Mac, it will run on Windows, it will run on Linux, it runs on NMR Box if you're NMR Box users. The NMR Box versions are not always as up to date with what we're putting out on our nmrfx.org website. So you could pretty much run it anywhere you want. So once you start it up, the first thing we're going to do is we're going to walk through a little work with sort of simulated data. So if we click on this processor button here, we're going to get a little tab, and this is where we're going to do all the processing stuff on a real data set. But if you don't have a real data set open, you're going to see this little simulation tab here. And so what we're going to do is just start adding operations. We build up processing for a real experiment. You're going to add in a series of processing steps. We're going to do the same thing with the simulator. So if I just click on the plus button, I can add in an operation. I'm going to use a shortcut as some commonly grouped operations. So I'm going to add these two, vecref and gem. We'll explain what they do. So every time you add an operation, it adds one of these little, basically called an accordion because it sort of you can zoom out and zoom in each little tab here. So the first one, vecref, is basically telling the simulator what frequency spectrometer you have. So basically it defaults to a 500 megahertz. How many data points you want to generate in the FID we're going to generate, and what the sweep width is, sizes, good Fourier transform people and move away from this. Nice power of 2, so it's by default 2 to the 8th, 2 to the 9th, and we have 512 data points. So that just sets up spectrometer information. Gem is where we actually generate actual sine wave. And you can see, you can sort of change all the things that you probably learned about at the beginning of probably in day 0 of our class, frequency, line width. So if I make you go over here to the auto scale line, so this gets better. So I can change the line width signal. And as you know, line width is basically the same as the decay rate, the inverse of each other. So if I increase the width of the line that we'll see in the Fourier transform signal, we increase the rate at which it decays. We can change the amplitude. Let me move my little chat here. Phase by default has a phase of 0. So this is actually not a sine wave, this is a cosine wave. So it's starting up there. And we can sort of play around and see what happens with the phase. So basically the phase is determining where in that sine wave you're actually starting. Very simple. If you were processing an NMR data set, what's the first thing that you might do? In a series of operations. Correct the phase. It's a little, I mean, for this, when we're looking at a single signal in the time domain, we can correct the phase in the way I just showed you. But actually, a phasing more complicated signal is we're going to probably do later on. So the first thing that actually get a list of operations, if you're processing, say, an NMR pipe, the first step is probably a zero fit. Let's go to common operations and we'll insert zero fit. So why do we zero fit? Two reasons. One, there's an aesthetic reason. Basically, the more zeros you add, the longer the signal is. When you go into the frequency domain, it's basically interpolating data points in between, giving you more data points. So there's a more esoteric and important reason. And whenever I talk about this, I go to my basement and I scramble through to find this paper that I've got stored down there somewhere, and actually found that Art must have put that same paper in the Dropbox. So if you look in the papers section, there's a paper on the Kramer's-Kronig relationship. Okay. So if you read that, it's sort of a pictorial tutorial. If you read that, you'll find out that if you have a causal signal, and NMR signals are causal, that is, this sine wave, before we actually did an actual pulse in the experiment, there's nothing there. So it's a causal response, an impulse. We have a pulse, and then we have a signal. If you're in the frequency domain of a signal that was generated that way, it turns out our NMR data is all complex. We can actually see that if I turn on some complex button. We actually have real and imaginary data points. The real and imaginary data points are not independent of each other. This is maybe a little bit of hand waving, but if you think about it from sort of how much information you have, if I take 512 data points, real and imaginary, you can think, well, I have 1,024 things I've measured. By Fourier transform that, I'm going to have 512 real and imaginary points in the frequency domain. But I've just told you that because of this Kramer's-Kronig relationship and causality, the real and imaginary points are not independent. If I get rid of all the imaginary points, I can recover the imaginary data points from the real points. So in effect, I don't really have the 1,024 pieces of information I thought I had. I really only have 512. So if you zero fill once, you basically end up with 1,024 points in the frequency. So you should basically always zero fill. Effectively, if you don't do it once, you're losing information that you painfully acquired. So that's step one. What am I likely to do next? Apodization. Yes. So what is apodization? So I'm going to actually change my little signal here, make the line width a little less. So you can see, if we look at the signal, we have the acquired signal, and then we've added these zeros afterwards. We have a sudden discontinuity between the signals and the zeros. That's basically like we sort of convoluted that signal with basically a square wave, rectangular wave, and the Fourier transform of that is going to give us a bunch of wiggles in our data set. So the next thing that we often will do is to do an apodization, which is some flattened form of removing the feet. So I'm going to go to common operations and introduce apodize. You'll see that I obey some rules in here. When I insert an operation, I try to figure out where it ought to go. So typically you do the apodization before the zero filling. So when I introduced it, it put it before the zero fill. You can actually degrade these operations around and reposition them. Open this tab, you see it has a bunch of subtabs because there are many different ways to do apodization. The simplest thing is an exponential decay, and basically that just multiplies our exponentially decaying signal by another exponential decay, and you can just gradually then drive the signal to zero. Exponential decay is reasonably commonly if you're doing small molecule NMR where you have very long signals that last a long time. NMR signal or macromolecular things, people seldom do an exponential decay. You can see we have a whole little family of processing. I think at some point I gave this demo and Art said, why don't you have the Kaiser function in there? So we added Kaiser function, and maybe so if I click, and every time you open one of these tabs, it assumes you want to use that and turns on the little checkbox. So we can actually turn things on and off. So I can see turn off the Kaiser, back on exponential decay. Kaiser, one reason why it's a good one to use. We'll actually show when we get into the FT. Actually, let's hold this off until we actually do the Fourier transform. So, okay, so next thing, Fourier transform. Why do we do that? If you look at this signal, I could figure out the frequency of this time domain signal pretty easily. I could actually get my ruler out and measure between the waves and figure it out. As soon as I start adding more signals in there, it gets so complicated that I can't distinguish different frequencies easily. So if we go into the Fourier transform, we move the data into a domain where we can actually pick out frequencies. So let's I'm going to turn off complex values for now. Let's go back to our plus button, common operations, insert Fourier transforms. Okay. So in the frequency domain now, if we're in Fourier transform, we actually have a signal at a particular position in frequency space. So we can just read off from the position the frequency. Why is there a little dip here? That's because the phase isn't right, because when I was playing around with phase, I didn't put it back to zero. So you can see this is what happens as we change the phase. We get different shapes. Basically, this is pure real, you could say, result of a cosine wave, and this is here. So we want zero. So let's go back and look at aptimization now that we can actually see things easier in the frequency domain. So if I go back to, let's turn off number one, any optimization. So now you can see these wiggles at the base. That's the result of the fact, again, that now we have this signal that doesn't decay all the way to zero. And so we have this sort of step function where we go down to the zero values. And you can play around and look. So if I go back to the exponential, okay, you can see what happens as I change this line broadening. As I make it bigger, make it very small, so there isn't any line broadening. And we have this wiggles back, so I make it bigger, the wiggles go away. But you'll note that the signal is getting lower and wider. So I'm basically adding the width of the signal is basically related to the rate at which it decays. And so by adding more exponential decay, I'm actually widening the signal. Let's go back and look at this Kaiser on. Let's just turn Kaiser on. So Kaiser on and off. Lower down that intensity there. So turn on Kaiser and compare that with exponential decay. You'll see that with the Kaiser window, I've gotten rid of those wiggles and have reduced the intensity less than I did with the exponential decay. The Kaiser has a sort of theoretical optimum that it maintains more intensity relative to getting rid of the sync wiggles, as they're called, compared to many other optimization functions. So that's a reason to use. Okay, you can get rid of the sync wiggles, less loss of intensity. Each of these functions has a different sort of effect, and depending on how your data is acquired, what you're trying to look at, some are better for getting rid of noise, because as you exponentially phase increase it, you reduce the noise. It also affects the width of the signal. So sometimes you just have to play around and see what looks best on your particular data. One of the most commonly used ones by people is sine bell. Yeah, so we can turn on sine bell. And very commonly used is actually sine bell squared. So this power basically defaults here to 2 if I take it down to 1. That's sine bell. This is sine bell squared. You can change things like the offset, and it's worth going back and turning off the FT, and then you can actually see what the shape of these functions actually are. We go back to and off the FT, put that to aptimization. You can see them. Basically, this offset for sine bell converts it from a sine to a cosine to a sine window. That looks sort of silly here, but there are experiments actually where the signal actually starts out in the indirect dimension experiments. It starts out at 0 and builds up. And there's some theoretical benefits of having your aptimization window matched to the shape of the actual data you're acquiring. So for this experiment, it looks silly to get rid of all this stuff at the beginning, but for a different experiment, it might be the appropriate thing to choose. So there's a bit of there's actual science involved, and part of it's in part of sort of looking at what looks good with your actual.
So Bruce, why is sine squared, really cosine squared,
Yeah,
become so popular? Because it's the same a Hamming or Hanning function.
Yeah.
Which is known to be bad.
not even that. I don't know historically how it became so popular. I'll say when I went to it, at your suggestion, when I went to Kaiser, I had to find a particular library that did the Bessel functions, because underneath the Kaiser is this a little more complicated. It's certainly more complicated to implement and code.
That's your
But
problem.
that's my
not a
problem, yes.
user's problem.
Not a user's problem.
The
Exactly.
problem
Yeah.
with the cosine squared, I mean, you're trying to get rid of the sync wiggles, right? It's a question of how much you broaden the signal versus how much of the sync wiggles that you keep. And cosine squared is known to do more broadening than needed.
Yeah.
So why people use it all the time is just behind it.
Which is why Kaiser gets rid of the wiggles with minimum effect on.
On the other hand, why don't you just program the Dolch-Schempp algorithms?
Yeah, well,
There's an actual I mean, there's actually an analytic result that is the minimum broadening to get, reduce the sync wiggles by a certain time. But it's kind of an iterative calculation.
And again, it does sometimes, it will show you when we get into processing, you can change these things interactively. Sometimes it comes down, you play around while you're looking at the spectrum and see for what you're trying to do with that particular data set. What gives you the best resolution of peaks relative to noise and intensities, and also depends on what you're trying to do. Are you trying to quantitatively measure peaks? Then the application is going to can affect the relative intensities of peaks in different ways. So a little bit of and it's what experiments you actually do. Okay, so there we are. We have signal. Yes.
Can you repeat what you said about the max acquisition window?
Yeah. So basically, I showed that example where we go back to Simon Bell, back to turning off the Fourier transform. I sort of made the signal start small and build up because I used this shaped window that actually starts at 0 and goes up. There are experiments you do that actually have this profile. Basically some cozy, traditional small molecule cozy experiments will start out with very little signal, and the signal grows and then decays away. In that case, it makes sense to use a window that has a shape similar to the evolution reaction. Significance. Not those experiments aren't as widely here. So let's turn off that sine bell window. Go back to our Fourier transform. Oops. Back on Kaiser. Okay. So we're now going to shift into something that's become a popular topic these days. If we went back and looked at the signal, I don't unfortunately show each individual measured point, but they're measured at uniform positions, which you can say in some ways is peculiar to NMR. Often if people are going out and doing experiments, you don't always measure, like you're doing a titration, you don't measure 1 micromolar, 2 micromolar, 3 micromolar exactly. NMR, when we enter the signal in the direct dimension, we measure uniformly spaced data points. And the reason for that is because when we process with a Fourier transform, if we don't do that, then we have sort of the same sort of discontinuities that we had when we didn't make the signal decay away to 0. We have all these places where you go from intense signals to 0 signals, and you end up with artifacts, the spectrum. So we do uniform. That's not a loss when you're doing a 1D experiment or doing the direct dimension of a multidimensional experiment. Basically, you can't, when you pulse and then acquire a signal, you can't measure this data point without waiting the time for that to evolve there. So you might as well measure all the points along the way. But when you're doing a 2D or a 3D or a 4D experiment, then every time increment in those extra dimensions is basically a separate experiment. You do it all as one sort of collected thing, but it's basically in the pulse sequence, it explicitly sets a certain delay to a value. And you could measure them, in fact, in any random order you wanted. You could skip them if you wanted. So there is no requirement based on the acquisition and the way there is in the direct dimension. You can actually measure them at specific discrete times. Why might you want to do that? Well, if I have to measure to get points out here, if I have to measure 128 data points, that takes a certain amount of time. If I could skip values, and one reason we go out in time is because the longer you measure, the better the resolution you get. So you want to measure out to a certain point in time. But in the indirect dimensions, that doesn't necessitate that you actually measured all the points along the way. So that's what is now the popular term of NUS, or non-uniform sampling. We don't measure it on discrete values. We can simulate that here. If we go to advanced operations, sampling, scheduling, okay? So now I've introduced an operation, a schedule operation, and by default, it's collecting 5% of the signal, so it could go up. That's the fully sampled data. And I can scroll down and get fewer and fewer data points, okay? So that's non-uniform sampling. Basically, it would be better if I showed you individual points. I always go back to zero, but these places where it's flat are basically data points that we haven't actually measured. And so if I measure, as I'm here, 8% of the data points, I can do the experiment in 8% of the time. So if you're time limited, you can get things done much quicker if you did this non-uniform sampling. There's issues, you're playing off between what the sensitivity of the sample is, requiring fewer data points, and you have less signal intensity overall. But there's no reason that you have to be constrained to measuring, when you do the experiment, uniformly sampled points. But if we do the Fourier transform of that, we get that, okay? So that doesn't look very good. What is all this? What I didn't sometimes simulate is actually we can go back to our FID, we can add random Gaussian noise to it, and we would get something that looks pretty much like this. This is not random Gaussian noise. Let me lower this down a little bit. Let me go back to my schedule. And I'm going to ask you a question. So right now we're at 8% sampling. If I raise the sampling up higher and higher and get closer to 1, what's going to happen to the spectrum? The noise will decrease. And the signal will increase. Very astute. You think that's really what happens? Let's find out. So here's the key thing. Noise goes down, signal goes up. Okay. So you're absolutely right. So this is not noise. This is not Gaussian random noise. It's not, I'm very fond of the fact that noise was named after me. It's not Johnson noise from thermal motions of electrons in the coil or whatever. It's actually your signal. And your signal isn't, instead of being here, it's spread out. There is something called the point spread function, which comes really from optics. You can think if you take a light beam and put it through a lens or an aperture and it spreads out after it goes through, how it spreads out is the point spread function. And so the stuff that is out here, the spread out, is actually, it's light, but it should have been at the center. So when we do noise and don't properly treat it, we're doing two things. We're increasing these streaks and noise in the spectrum, and we're actually reducing the intensity of the signal. So when you adequate NUS processing doesn't just get rid of the streaks and noise, it actually puts the signal back.
Does that mean we need to reconstruct all the shattered signal into one?
I mean, effectively, that's what you would like to do, is reconstruct. And so what we're going to do, there are a bunch of different algorithms. What we want to do, in effect, if I go back to early sampling, we have a lot of zero values. One way to think about this is we want to estimate what the values that we didn't measure actually are and put them back in. So that's what a NUS processing algorithm does in effect. There are multiple ways of doing that. So let's go to yes.
So I noticed that when you change the sampling schedule, spectral width did not change.
Yes, I'm just choosing a random population of values that I'm setting to 0 in the simulation.
Okay, so the right time is affected.
Yeah. Dwell time, all that's unchanged. There are many ways when doing an experiment, there are many different ways to decide what points to measure, what points not to measure. I'm just specifying a certain fraction, and what I'm defaulting to in here is something called Poisson gap sampling. And you can see just looking here, there are more points that are measured near the start of the signal than there are measured out here. And that's a property of Poisson gap sampling. Depending on what reconstruction algorithm you can use, you can have better or worse choices of what the sampling schedule would be, but Poisson gap is probably the most widely used. So I'm going to go back to advanced operations, and I'm going to insert green. So so you can see the only thing I've done here after the schedule is I've inserted one new operation. I can turn that off. It looks like that. I turn it back on, and basically I've reconstructed the missing data points. Grins, for those of you that actually done this, used NMR pipe, you might have used a program called Smile for the NUS reconstruction. Grins is my recursive algorithm for Grins is not Smile, but it's kind of similar. Maybe it doesn't work quite as well, but it's pretty.
Yeah.
Simon's working on past unit and stuff like that. Especially if you're not really down in the weeds of how much sampling you are, we're pretty simple. But there are a bunch inside the NMR effects. There are the other ones. There's IST, which was one of the earliest programs that people used to center iterative soft thresholding. There's Nest A, or the Nesterov algorithm. So those are other options to use. Grins in our hands at the moment seems to be working best for us, but we can go back and look at it in the frequency domain. So it's remove grins, looks like this, put grins back in, looks like that, okay? So if all data was that perfect, grins would be that perfect as well. Let's see. Trying to think, I mean, basically processed the spectrum at this point. One thing I want to call your attention to, will it show up here? If I go back to apodization, we'll go back to Kaiser. There's a pretty small. Let me zoom up. Okay, there. So all the apodization functions have a parameter terribly named C, which goes, I can't remember, pipe uses C. Pipe uses C, and I inherited, I tried to make this look comfortable to the pipe users. So what is C? C, I showed you the apodization window, different shapes, the Kaiser shape, the sine bell shape. There's a special treatment that you might want to do often to the very first data. Don't have a nice picture of this, but you can think of, when I showed you the FID, you've got all these points with little spaces around there. They're each measured at a certain time delay in between. The very first data point effectively has half as much. If we're doing an integral over things, the window we integrate over is really half as big for that first data point, because the other half of the time of it is the time that comes before time 0, which is, we talked about causality, doesn't actually exist. So that data point is excessively weighted. It's counts. You know, you think we're doing the Fourier transform as an integral, it's getting scaled up more than it should, twice as much as it should. So C is a value that weights that first data point. And what you can see is the effect of changing C is to change the baseline. Change this intensity of that first point, shifts your baseline up and down. In the direct dimension, actually, that first data point is often corrupted by, bringing you to the probe and all sorts of things. Doesn't mean, C is less clear exactly what it should be there. Typically, just leave it at 1, worry about baseline correction if we need to. But in the indirect dimensions, then C becomes very important. If you don't set it 0.5 in most experiments, then what you find actually, the first data point controls the over integral in the Fourier transform. And so basically, it shifts the entire spectrum up and down. And it shifts it up and down in a way proportional to the intensity of the actual peaks. And so you get some peaks going up and down different amounts, and you get these bad streaks through the data, so-called G1 noise. So it's important in those experiments to set C down to 0.5. Now, when would you not do that? Sometimes people do an experiment where they actually, that initial time period in the indirect dimension is actually half of the dwell time. Two consequences of that. It messes up the phase, because that phase issue we saw comes about because of delays in acquisition. And you went up to correct the phase, you need to have a 90-degree zero order and 180-degree first order, because you haven't really talked about phase correction. And because you delayed it, now that point it effectively is represented by the same width that all the other points are, so C should not be 0.5. So basically, depending upon if you acquired a data set that requires an 180-degree phasing, you're going to set C for 1. Okay. Gosh, we spent a lot of time on just one FID, but you're going to end up processing millions of FIDs. So knowing how to get one right is going to help getting the remaining 999,000. Okay. So I think that's a good place to stop on the simulation. Sort of gone over the basic function. We'll cover some more as we get in. But you can see if you go to this advanced operations, there's many categories. Each category has multiple operations. So there are many more things you can do. But basically, you're going to take your signal, you're going to zero fill it, you're going to rapidize it, zero fill it, Fourier transform. So that's where we are. Okay. Any questions on that? Any questions out in the Zoom world? Okay, let's move on to actually some real. Close up this processing window. We should be good to just start. So multiple ways to open real data sets in here. One, we can go to this file open menu, or there is a little box here for data sets. And in data sets, I can go and I can browse to a folder. So I'm going to go to inside that Dropbox folder. There was a folder called NYSDC1. Which I can't see because this is this is my test one. The reason it's not there is because I probably dragged it into the Dropbox, and that dragged it off my computer, which I find annoying. When you go into Dropbox, you seldom want to delete what was. But NYSD, well, actually, let me actually go to the Dropbox folder and get it from there. The only difference in these is that I've already processed the ones in the test one, and so I want for the demo of this, I want to be able to start with. So we can pull down the options. Right. Okay, so if I do that with a click on the datasets browser button there and go to a folder and click open. If you've already got the folder, you hit the index, it basically goes through that folder and it finds every NMR data set, raw data set that's in that folder. And it'll find subfolders within some subfolders. So if you actually do it to the home directory of your computer, it'll find every NMR data. You can't go on. It will find every NMR data set on your computer. This is the name of the FID. This is the date it was acquired. The fact that the data set column is empty is because we haven't already processed this data, so there isn't a processed data set in there. If this is Brooker data, and it will actually find the 2RR, 1R, 2RR processed files in there. Here's the pulse sequences. So let's just start. Let's start with ubiquitin relaxation 1. So if I just double click on that, and I'll say I'm going to change the GUI here because I don't. So it's like this. If there is a data set there already and you double click on it, it'll open up the process data set. If you want the FID, you have to hold down the control key. I'm going to make it so there's explicit buttons for that. But since there isn't a data set, double clicking will open up the data set. And this has a mixed going to it. The first thing it does is it's going to ask you for the name of a data set to process, to put process data in. By default, if it's Brooker, it takes the root file name and the Brooker number. So this is, it's going to call this, you get RLX_1 because it was Brooker data set 1. Let's all say save. And lo and behold, it's processed that data set. So we didn't build up any operations. That's because for a 1-dimensional and a 2-dimensional data set, it basically looks at the parameters. It takes a guess at what a good processing script would be. So if we go over to the processor here, now we can look in dimension 1 and introduce application, zero fidelity, Fourier transforming, phasing. Come back to this, it's not properly phased. If there's grayed out, there are things I put in that I think you might want to use, but I don't necessarily want to turn on. So like signal suppression. So what is this? Water. Yeah. So maybe we don't want water left in our signal, so we can go to signal suppression, turn that on, and the water's on. Okay. Let's take a step back and look at a little bit more of what is actually done. So I'm going to go up here first to the parameters tab and see what's there. So we just get a list, what's the pulse sequence, what's the solvent, what's the temperature. That's the temperature recorded in the Brooker ACQ US file, which is not necessarily the temperature of the actual in the probe. The data was acquired. Output type, you have 3 choices. NMR effects, which is actually my old NMR UJ format, UCSF, if heaven forbid you want to use Sparky program. It likes the UCSF format. Spinit is the commercial rights of the software is now owned by a Canadian benchtop NMR company. Everyone's part of a Swiss NMR company, and they have their own processing software called Spinit. So that's the Spinit. So it defaults to NMR effects, acquisition order, maybe we'll talk about later. And we get information about each dimension. How many data points, what the spectrometer frequency is, sweep width, things like that. The important thing is the acquisition mode for the indirect dimension. Have you talked about echo, anti-echo, and
Just
a little bit? Yeah. So let's go to close up parameters, and down the bottom of the window is this choice where you can see FID. So there's the actual original FID for the first row of the data. Bid with ops is the FID with all those operations I showed applied to it. And spectrum then would be fully processed. So let's go back to parameters. This could be a little bit glitchy. We have some choices here. Yeah, that could work. So default acquisition for many years in NMR was something called hypercomplex. In order to get frequency discrimination, positive, negative frequencies in the indirect dimensions, and do it in a nice phase mode. The idea was called hypercomplex or method of states, was developed. And you acquired two experiments. We call them the real and imaginary. And then you process them. You take the real values out of the first row and the real values out of the second row, and those became basically the real and imaginary points. It was realized quite a few years ago that if you acquire an HSQC experiment, you lose part of the signal. You roll these pulses at the end of the process, you've lost some of the signals. And so one term for this was, I think, preservation of equivalent pathways. So you actually can do the experiment in a way that at the end of the experiment, you can keep all the intensity instead of doing, pulses where the phases end up getting rid of the signal. Then at the end, you have to recombine the signals in an appropriate way. And it turns out that what you do is you take the first row and you subtract the second row from it, and that becomes your new first row. And the second row becomes the first and second row added together. So some linear combination of those. That method is also called echo, anti-echo. And so if I go to echo, anti-echo, watch what happens to the peaks. Basically twice as big, because we've kept these two pathways. What's that going to do to your signal to noise? Which is what we care about a huge amount in markets we never have enough. Will it be twice as big? Square root of 2, yes. The signal's gone up twice, but because we've co-added noise, and the noise adds in a way such that we gain square root of 2, but still square root of 2, like 1.4 improvement in signal noise is quite a bit. So echo, anti-echo has become pretty standard for these types of experiments. Okay.
So,
Yes.
I wouldn't use echo anti-echo if I'm not doing preservation very well.
Yes, you would typically just use the hypercomplex. I look at the Brooker parameters. There's an FN mode parameter, and it should be set appropriately so that I can detect the correct type to do. But you can have a parameter set this way. You can write a pulse sequence to do something completely different. So it's not always possible to figure it out correctly. Okay, so let's go back to dimension 1 here. Look in this mode, the operations we can do. So signal suppression, you can see there's the water signal and turn on signal suppression. It actually does a fit to the FID and removes sort of the dominant decaying signal, which is often water. You can change with this shift exactly where it's suppressed, because you might have not only water, but you might have some other detergent or something that gives you a large signal that you also want to suppress. And you can add multiple, you can add as many of these operations as you want. So you can signal suppress it in different positions. Okay, haptization, terrible, but I've defaulted to sine Bell. We can go to Kaiser if we want. We can play around with those Fourier transforms. So phasing. This is the other clear problem with the signal. So by default, I don't auto 1D experiments by default. I apply some auto phasing. 2D, I don't. So we can just slide phase 0. Get it right. Now there's phase 0 and phase 1. Phase 0 is what we sort of saw in our simulations that didn't simulate for you very first order phase correction. So phase 0 means the phase correction, the co-adding of the real and imaginary data points to give you nice symmetric peaks is the same across the entire spectrum. But there is often also an effective phase that varies linearly across the spectrum. So phase correction might be 0 here and it might be 45 degrees here. Modern spectrometers, good pulse sequences these days, in theory, you shouldn't really have a first order phase or even a 0 order phase correction in the indirect dimensions. And you shouldn't really have much first order phase correction in the direct dimension, but you may. And so if to do that, there's some of these operations have some additional buttons in here. For example, this pivot button. There's various places in NMRFX where you see a menu button, a button with a menu beside it. So if you click the button, you get what is the first thing in the menu. If you want something other, you can pull down the menu. So the default for pivot, if I click, is it's going to find the most intense heat and set a pivot there. And what we do, which is not necessarily what you want to do with this complicated spec, you might want to actually set it over here. So the alternative is actually to click on the crosshair button down here at the bottom. And now we have a crosshair, and we could set the crosshair on this peak, and then go back, choose this menu, and say set the pivot at the crosshair. You see the little green triangle pointing out where the pivot is set. So now we can adjust if that peak in phase. That's all this spectrum actually really needs. But if we needed, and this was out of phase, we could use the first order phase correction to adjust the phase in other places. And you'll see the phase at the pivot is not changed. Okay. Okay, one more thing. This is a proton nitrogen HSQC protein. Pretty much all we see are amide protons. So even though we sat on the water, is a common thing to do, we have a huge amount of space in the spectrum that is a field of the water. And why carry that along with us? So I also add in an extract. And as a default, we can open that up, turn on. So now we've extracted the left side of the data set. We can be more explicit. We can actually put up the region, and we can go to our crosshairs and set the crosshairs at specific places, and then say add region. And now it's explicitly put in the PPMs, the start and end. Okay. So that's dimension one. Dimension two, basically, this is, I don't know if I've seen any other software that does this. What we've done is actually we've gone out and found all the data points, the first data point in each FID, and extracted the data point. So this basically would have been as if an FID in the indirect dimension, and we can apply the processing. So here we can actually see what the processing of the nitrogen dimension looks like. Sometimes the signal noise is such that you can't do anything useful here, but you can actually see signals there. You can see it reasonably well phased. You can look at the operations of on-here optimization, zero filling, Fourier transform. I just add some basic defaults. So now if we click process, it's going to apply the processing scheme, and now we have a nice process scheme. Okay. I can go up and down. All these buttons I've already talked about over here. Lower. Higher. Another way to look at this, we go to stack plot. This, I think Art likes to tell the story of looking at somebody's data once, and they had beautiful contour plots, and then I think you went down to contour level and actually saw there were all these artifacts. The stack plot is nice because you can actually see. So you can see all the crud that's maybe just below your chosen contour level. And we've made it, tried to make it fairly simple to go back and forth between contour and stack plots. There's also traces, which is just a single row. Contours, the contours. Okay. Couple other things. Let's walk through the rest of the options here. There's actually full data set. There's only one operation that actually has currently full data. So this is something that instead of happening on individual vectors and you repeat it over and over, it's something that looks at the entire data set. So the one thing I have there is this D phase. Let's go back to dimension one and let's turn off the phasing. And you'll see that at the bottom of the screen, there's this auto update button. If auto update's on, then everything you do will immediately cause it to reprocess. And that for 2D, that works pretty fine because it's taking like 300 milliseconds to process. So I can look at, I can turn on and off phasing and immediately reprocesses the whole thing. So if I turn the phasing off, so this spectrum is no longer has the phasing that I set up, I can then go look at what happens in full data set mode. If I turn on dephase, this is fully automatic phasing, looking at the processed data set. And it's for a good quality data, for a data set of reasonable signal noise, it's pretty good. It's often will be as good as if dim is set to 0, it means do both dimensions. If I actually set it to 1, that's only processing dimension 1. So you can, in fact, see if I only do dimension 2, it's not auto phasing the first dimension. Go back to 0. It's both. By default, first order phasing is turned off, but if you turn it on, then it's going to actually optimize the first order phase correction as well. So that's full data set. Dimension 1 post processing. After we've done all the processing, we go back and scan through each vector and do some additional processing. Typical thing, we might do some baseline correction. We fully got processed, and we might want to go back. This data set, thanks Shivani for collecting these beautiful data sets. Thank you, Ubiquitin, for inventing itself. Beautiful protein. Doesn't need much. Actually, it's turned. Actually, I have it turned on. So the default here is BC width. If I turn it off, we're probably not going to see. Oh, okay, there's, so I go up, there's some stripes through. If I turn on BC width, boom, they're gone. Okay. So BC width is baseline correction with the Whittaker perfect smoother. If the only thing you turn on here is it does an automatic region finding where you don't have any control. If you turn on this auto regions, then there are various parameters here to control how it's choosing what's baseline and what's not. But these things, again, because we made the processing pretty interactive and fast, and you can just sort of, play around with things and see what looks good and what doesn't, especially for simple spectral like this. Okay.
What window function was applied?
Yeah, my default, I think I actually went back and changed the default in part because this is what 99% of the universe is coming from pipe uses sine bell. So I think I default putting in sine bell, but we went and manually added Kaiser. But we can we can zoom in, and then we can actually play around with the optimization function and actually watch what happens, because it's pretty quick at doing the full processing. So we can play around with this offset parameter in Kaiser, the power in sine bell, etc. Let's show one more thing, which I didn't turn on here by default. If you look at the processing for dimension 2, you'll see something called extend. So if you think of the NUS processing we looked at, we described a scheme where you randomly didn't measure certain zero values. For years, there was a use of a technique in NMR processing called linear prediction, where basically you didn't have enough time. You measured 120 indirect data points as long as you had to wait or as long as your protein would stay around. Linear prediction you used to then sort of extrapolate what the signal would have been if you'd measured it. Typically, you might extrapolate out twice as far. Can't remember who originally came up with the idea. I know the Smile paper talks about it, but other people talk about it. You can think of that as basically you could think of adding zeros at the end of the spectrum. Think of that as just a NUS processing. Instead of randomly choosing zeros at different points and dropping them out, you could just add a bunch of zeros at the end. The advantage of that, you didn't have to do any sampling up front to decide when you acquired the data set. You come afterwards and think, I'd like to extend this data. We can just pretend that it was a NUS experiment, but all the zeros were at the end. So we can actually do that to the data, even though we didn't do NUS sampling up front. It's not going to be as good probably because you can think of typical NUS processing as interpolation. which is always typically easier than extrapolation, which is why we're not all rich in the stock market, because we can interpolate what the price might have been yesterday. We didn't know it, but knowing what it is next week is harder. But if we turn this on, watch what happens to the signals. Boom. Okay, off and on, off, on. Okay, so we basically use in this processing. I think if I go here to extend, it's defaulting to nest A, but we can change to the grins. And it's basically treating it as a NIST problem and stuff. And you will see a narrowing of your lines in the N15 dimension. And we'll try to make this stuff easy. You know, look at Biden and see if it looks better. Doesn't look better, turn it off. Experiment with apodization schemes and you know, show up your phasing, etc. Interactive. Okay, so now we've got process HSQC experiment. Questions, where do I want to go next? I can do some more stuff with this experiment, or if you go off to a 3D experiment. Let's just,
I have a question.
yes.
Is it possible to look at the T1 program?
Yeah,
T1?
yeah. Not as well, I mean, that's effectively, if I go to bid with opt, or if I go to bid and choose dimension 2, this is before any processing. So and there is a tool down here called the navigator, and it lets us scan through every slice to actually see after you've done the first dimension processing. You can do that not as nice as you should be able to basically go into dimension 2 and turn off all the processing. Unselect everything and then hit process, and you will end up with only processing the first dimension. And then you can do a slice. There's a slice tool you can put in. You can do a slice. So that effectively gets you. I will say this navigator, one thing we added just to, you know, like I want to highlight things that are there. Corrupted index ID. Sometimes people will collect an experiment for a week, and there was a power glitch or something, and like one data point in your week-long experiment is corrupted. We can apply the same idea that we did with NUS and this extension. We can say, well, let's just set that data point to 0 and treat it as a NUS problem. We basically use the NUS algorithm to predict what would have been there. This corrupted ID thing, if you scan, it will go through and find FIDs that have much larger signals than everything else. And then you can insert basically that extend command and it will fix your experiment. I mean, I did that. It was a group, Park University, I think. They came to me and they collected all this data. It was all useless because it was all corrupted. We were able to go in and fix those data points. So that's the hand thing. This little scanner then lets you also scan through and actually visibly look for fits it. Okay.
I have a question.
Yes.
So it only read the temperature from the serial file to the spectroscopy.
Yeah, it reads out of the ACQ-US file.
Yeah.
I can't remember what the parameter in there is, TE, which is what you set
On the spectrum.
on the spectrometer. I can't remember, Brooker, if there's a way to, is there a way to get what it thinks the temperature of the probe is, or can you only get what?
We change the temperature setting from here. I don't see.
You can't, those fields are not changing. And it's actually a request. One example is my referencing, which I haven't really talked about, depends upon knowing the solvent. And there's some group had some stuff that had EMSO in the sample and made the solvent, made me not think that the solvent was an aqueous sample. And that changed the way I did the referencing there wasn't an EC. They went into the ACQSFS and changed the parameter there, and then it detected this, correctly, but I need to make these changes, so you'd like to give it. There's not a lot, well, what matters? How is temperature used? The way it's used, and I haven't really talked about referencing, is that if I go to reference, if there's nothing in this field, if it's empty, it tries to figure it out from the parameter set. And parameter sets, for example, they're better at being able to do that. But an alternative way is if we went back to that first row we were looking at, we can say, I want to set the ppm at center and say that it's H2O. And if that's the case, I look at the temperature and say, what is the chemical shift of water at 303 Kelvin? And set that there. If that temperature value is wrong, then I'm going to give the wrong reference value. Yes, so I should make it so you can actually correct. If you do HGO ppm, it actually tells you that it thinks center temperature is at 4.774. You can do the correction yourself.
Because some of the magnets in maybe 800 magnets, we need to correct calibrate the temperature using the temperature. And that's different from the actual sample temperature.
Yes. So that's a really important reason why I need to make this editable, so you can go. Of course, ultimately, the only thing that it affects currently is that it's going to affect my calculation of the reference. But that's pretty important. Okay. So I'm going to leave this window up to show you, for example, that we can actually go to Spectra, new window, have another window up, and in there I can go to Open, and I'm going to go to Data, no, Demos, NYSBC1, HNCACB, NUS, and I'm going to choose. So now I'm showing you to actually manually go through. If you actually manually go find a file, what you want to do is find the SER file on Brooker. If it's 1D, it's going to be an FID file. Find that file, click Open. There it is, because this is a 3D data set. I'm not confident that I can come up with a processing scheme completely automatically. So I didn't automatically set up the processing. So if I go to the scripts window here, I can say auto generate, and it will then automatically generate. I just don't do it. I don't automatically auto generate for 3D. It will set up a processing scheme, and you can go look at it and see what it did. And here's the key thing. It looked at this experiment, and see, this is a, okay, I want to get rid of that. It looked at it and found that there was a NUS list file. Decided that this was a NUS process data set. And it should, in the recent version, also look at a Brooker parameter and say, yes, it was collected with NUS, because sometimes people have fully sampled data sets that actually still have a NUS list file in there, but really weren't NUS. And so it automatically introduced the current automatic things, nest A, probably change that to grins. And so let's see how that, if I just hit process, it's going to go through for 3D. So it processed the first dimension, and now it's got indirect planes, and each indirect plane, basically think of it has holes in it from the NUS sampling. It's fixing those holes, basically replacing those values. When it's done, then it's going to go back and do the conventional processing on those two, on the nitrogen and carbon dimensions. So this step takes, this is a little bit slower, because it's basically doing about 500 forward and reverse Fourier transforms in this algorithm. I'm not convinced that this automatic generated one is going to process exactly correctly, but let's see. from memory, it's something like this data set, this is look right. Let's just see. While it's running, I can go look and see, basically, the only difference 3D is it added a third dimension tab that has the processing for that dimension. Okay. So there it's processed. So this is a 3D experiment. So now we have an additional control over here called Z for the third Z dimension. If I say full, okay, we're seeing all the planes on top of each other. Okay, so actually I didn't phase or anything. So I didn't set up the phasing. I didn't want to take the time. But you can see it basically processed that. I didn't get rid of the water because the auto generate script doesn't introduce the solvent suppression. I didn't introduce the extract and take out. And it's actually important for NIST processing. You're basically processing each one of these planes for the NIST process, and there's no reason to be applying that to all these planes over here. So it's good. This is a good reason to sort of just extract the region that you want in your direct.
Is the nitrogen dimension upside down?
It's very possible. It is. So let's talk about that. We can look at these two buttons, X and Y, now appear in 3D. So we can actually put by default, we're actually seeing, yeah, we're seeing proton, nitrogen, yes, and it looks funky. So what do you do to turn around a spectrum? Two ways to do that. Generally, I get this right. If I look at the Brooker parameter files, I get it right, so it's the right orientation. But again, you can write your pole sequence in any way you want, so the parameters don't matter. So two ways to turn around. There is actually a reverse command that just reverses it. But Fourier transform, if you negate all the imaginary data points, so multiply them by -1, that will reverse the signal. So if I go in here to Fourier transform in dimension 2, you can see that in fact, I've turned on two options. Negate imaginary does what I just described. Negate pairs actually negates every other pair of data points. The effect of negate imaginary is to reverse the spectrum. The effect of negate pairs is to shift the spectrum by half a sweep. And both those may be necessary depending on how the data is acquired. Like I say, for a modern Brooker experiment, where the pole sequence is consistent with what's in the parameters, you shouldn't have to do either one of these. A little easier if I actually went back to see that. Let's go back to our HSQC and go to dimension 2 here to be faster. Go to Fourier transform. You can see it came up with a negate imaginary. Let me turn off negate imaginary and boom. Off, on. Boom. Just flips it, okay? You get used to when you looked at a lot of spectra, you get used to the fact that proton nitrogen, HSQC, or that dimension of 3D has this sort of tendency to move from the lower left to the upper right. It's almost like a typical slope to it. And when it looks like that, you think that it just doesn't look right. And but you know, you just get used to it. It's just the chemical regions that amino acids appear in as such. You get that. But here, if I turn on negate pairs, you can see, boom, it's basically shift to have a sweep with and wrapped around to the top. So if you see, if it looks like this, then it likely means you need to turn negate pairs on. Reading. I just want to show you a few things, obviously I didn't do the phasing, I didn't do anything. I don't want to take the time to do it, but it's pretty quick. I just want to show you a few things you can do in a 3D. By default, I showed, I did full here, but I can do center. And come on. Now I'm showing the center plane and I can just scroll up and down through planes. That way, I can look at any orientation of the data set. So if I change X to put nitrogen on the X-axis, now carbon's on the Y-axis. It looks terrible because now the planes are proton, and I didn't get rid of the water. So there's a plane in there that actually has water. But it shows you how simple it is to sort of flip around. You can show the data set in any orientation. Maybe I just show this data set. You could make it nicer just by going doing the extract and stuff like that. But the point is the 3D, you don't get automatic script generation, but you can automatically generate it, but you're often gonna have to go in then and tweak it up a little bit. I will say, let's just do one thing. If we go to the scripts panel, when you process the data, when you set up all these operations and process the file, what it actually does is it writes a script in Python. It won't work in just native Python. It requires the tools that are inside NMRFX. But you end up getting a script in Python in the same folder the data set was in. And you can go and load that up. So I'm going to go and click on open, and I happen to have in that folder, I have a script called process_works.py. So I'm going to load that in and now hit process and see if that looks better. I like to, once I get something that looks good, I like to save. So there's actually a command in there in that menu. Let's go back here to. So now this is actually the proton carbon view. Go back and show. There's the. So that's proton carbon. There's proton nitrogen. In the scripts menu, you can save files. So after when something looks good, I'll save it under some name besides process.py, because every time you hit the process button, if it's successful in processing, it will write a process.py and replace what was there. So if we get something that I like, I'll save it with a different name and then I can load it in. You can take this processing script and open it in another data set. The processing script will have in it the name of the FID in the data set, but those are sort of thrown away when it's read in. So you can open another FID and then click the menu and go find a process script from another experiment and read it in and apply that. So once you have a good script for a type of experiment, you don't have to keep recreating.
We look at the script itself for a moment.
Yes. So if we go to script, show script. There it is. It was for a while. I made this editable, and I'm going to bring that back so you can actually go and look at it. So some Python stuff at the top, an FID command to tell it where to open up the file, a create command to tell it where to put the MV file. Some things that are referencing acquisition order, important to broker data sets, acquisition arrays, I will get to in a week. A lot of stuff. The fixed DSP I haven't talked about. Zero frequency labeling. And then finally we get down to DIM1. Then everything that comes after DIM1 are the operations that happen in just one. DIM2, 3 is where the NUS processing happens because it's using both dimension 2 and 3. And then you go back and do dimension 2 and dimension 3.
And now acquisition mode.
Acquisition mode, yes, complex, hyper. So that other experiment would have had complex echo anti-echo -r. I used to actually put in an explicit operation that did those, and I decided it was easier to sort of define those as parameters for how the data set was collected. There is still a time domain combine operation that will do it, and basically putting those in sort of tell it and insert that operation. But yeah, you can go and if this won't run in Python itself, you could go and edit these back like we were doing in NMR pipe script, edit them. You can run them from the command line. You can run NMRFX from the command line. So you can type NMRFX A, you'll have that set up and give it the name of the script process without ever going into the GUI. Okay, we're of course not out of time. gonna look through a few things that I want you to be kind of familiar with. We haven't talked about ring at all. Of course. So
In principle, there's a problem session after this, which isn't happening. So you can go a little.
I could go on, although you also would talk about showing some prosy stuff as well.
We don't have to do that.
And I will stay around as long as people find it useful and have time. So all we've talked about is processing. Let's talk a little bit. I don't know who's out in the world. What type of NMR?
Your
Nucleic acid. Okay, so
protein solid state.
protein solid state. Okay, nucleic acids. We have a lot of stuff in nucleic acids, but we won't. That's a day. But I'll show you a couple things in a second. So first of all, let's talk about more and more things that are going to appear over in this tools panel. So the simplest thing you might want to do is pick specimen. Okay. If you want to do that manually, we can go into a region and there's actually, if I'm in the selector mode, there's cursor mode, which you can do things like put the cursors up, crosshairs up and expand. And come on, make this thing go away. Yeah, move. This is in. Okay, in selector mode, I can do things like drag out there and zoom in on that. I can click on a peak, move it around. I can pull down the option key on my map and resize it. In peak mode, I can go and click and pick a peak. So I can, instead of automatically picking everything, I can go through and individually pick things. I can move that guy again. We're working slowly on a more complex peak picker these days. But you will find the current one just looks for local maxima. So a place like this, it found only one peak. If I hold down the shift key when I do pick, then it forces it to pick exactly where you clicked. If you don't have the shift key, it actually searches and finds a local maxima, and it would have gone back and found the original peak. So that lets you have, you know, explicit control over where saw just speaks. That. I'm going to repick everything. I'm going to show you a couple more things. Oh, exception details. Okay, if you click pick, it's got this mode new, and it's telling you that there's already a peak list there, so you can't pick. I brought that back in, so you nucleic acid people may know Victoria D'Souza. I was doing a workshop on how to use NMRFX in RNA stuff, and she'd done all this peak picking and assigning, and then I had a pick button down here at the bottom, and she clicked that pick button and blew away everything she had done for the last 20 minutes or whatever. So we've gone back, some of we had an NMRVJ, this more full featured pick tab, and by default the mode is new. If you hit pick again, it won't let you replace what's there. You have to explicitly say, I want to replace this, then pick. Pick and replace what's there. I'm going to remove this peak list. So I went to a content thing, which where there's controls over what data sets. You're going to have multiple data sets in a window. You're going to have multiple peak lists in a window. I'm going to remove that peak list, and I'm going to feature something that Ellen in the back is working on. So we don't have time to talk about assigning proteins here, but oftentimes these days you're working on a project where maybe there's assignments already. So if I go to projects fetch star 3, Air content already present. Okay. That's something we're working on. Basically, when you save a project in NMRFX, it saves everything in a BMRB style star file. And we can now go, we can just say fetch and go to the BMRB and pull down a star file. And it's basically, that warning was like, I've already got work going on. I don't want to blow away everything I've got. We're adding, soon adding the ability to just say grab the chemical shift assignments and stuff. Not everything there. I'm gonna manually, let's see if this works. Open star file, I'm gonna go to demos, I'm gonna go to NYSBC, and I have a VMR star file. Yes, that opened it up. It didn't complain. So if I go to the molecules menu, there's an atom table there, and what we can see is it read in that star file and it got the sequence of ubiquitin, which is what this data is, got all the chemical shifts of ubiquitin, got all that stuff. There's lots of little tricks. This is a lot like that. We can come over here and see the sequence. We can go here to secondary structure prediction and click display. Everything, Chat GPT, everybody's talking deep learning these days. So we're doing a lot of stuff in deep learning. So that's a deep learning secondary structure that looked at those chemical shifts we got from the BMRB and gave us a prediction of the secondary structure. Based on it. So red's helix, blue's G. It's basically a probability that.
Based on the CSI.
I mean, it's the same idea. It's based on the chemical shift deviations of each of the main atoms in each amino acid. If you're doing sort of disordered proteins, I can go back to molecules, atom table, and say that the reference to be random coil peptide shifts, and we use an algorithm that was published by Franz Mulder, I think, and then we can say do that, and basically the height of these dots is an indication of the order of that region of the protein. It's either D-terminus, it's more disordered, and there are little disordered regions in between the secondary structure regions, etc. But what I really wanted to do was, now that we have chemical shifts in, we could go and we could say simulate a peak list. And I can say, I want to simulate it HSQC N15. I want to simulate it relative to my ubiquitin data set. So I use the sweep with the chemical and spectrum frequency from it. They generate, created 88 peaks. There's a table of the ones that it created. And we can now go to peaks over here and say, I want to put that simulated list on data. So you can see there's a little reference difference, but things are pretty close. This is not collecting our exact same conditions.
Maybe center based on just the repeatedly just centering.
Yeah.
From the existing.
Yeah. So one thing I can do to fix is if I'm in selector mode and hold down the shift key and I drag across the whole spectrum, now I've selected all the peaks. One thing I can do is now I can click in one and I can drag them all, get them close. There is a technique under peaks here, tweak all lists. Tweak means if a peak is overlapping some signal, it will find the maximum where it overlaps and it'll move that peak to be there. Well, let's do something a little fancier than that. Here's a tool for the RNA people, really, and we don't have time to show this in the RNA mode, although there's videos on our website. If I pull up this peak slider, I click on a peak, I can slide it into place and click tweak and freeze. It's tweaked that peak to find this exact position, and it's frozen in place. It's turned red, so I know that peak now I've manually moved in place. But this is where we cross our fingers. We've peak picked this data set. And now we've also generated, yeah, I have this ubiquinolix where I've actually peak picked it, and now I have the simulated list. What I'm gonna do is I'm gonna match the simulated peaks to the nearest real peak and try to move them. So if I go to actions, perform match, boom. Okay, everything that's red, it decided was isolated enough that it was unambiguous where the nearest real peak was, and it moved it. You can see this guy was too far away. This guy's, there's sort of actually two peaks overlapping there, but we've got a lot of stuff moved in, you know, is probably correct, and things that that it was uncertain about in overlap regions. It leaves to you to go and decide where to put them. But the idea is it can get a lot of stuff. And this is a common scenario these days. So many approaches have been assigned already that
If you lower the contour, there's a couple of boxes that don't show a peak.
yeah,
Lower the
yeah,
contour.
yeah. So maybe this guy, and up here maybe this guy. So maybe we want to do that. Problem is, if I got that low and did the whole repeat picking, I'd have so many things.
Right.
And
And then you raise the contour a little.
yeah. Uh-huh.
No, the other way.
Oh, the other.
So you see it around 7.2 and maybe 122. There's
Just
four peaks that aren't
One.
labeled at all. Anyone know what those are?
Those are. Argent.
And those are arginine and epsilon
Yes.
that got folded in. They're really up at, I don't know, where they
Yeah.
80 or something. So hopefully in your sequence, there's more arginines.
Yeah, we could go. Yeah. I need to have little tools. Many things the listed actually gives you the amino acid counts. 1, 2,
3, 4.
3, 4.
Yeah.
We can count. Yeah. One thing you'll see up here, if you click in this slider tool, which is really developed for, actually it was really developed for cyclic peptides, but most widely used for RNA, widely used in Mike Summers' group and his descendants, etc. If you click on these guys, you'll see it actually, well, actually, that's frozen. It's actually knows that these peaks are related to each other, has a line between them. And for some reason, it froze one of them, it didn't freeze the other. If I go over this guy and thought, you'll see that I can move these guys together because it knows they need to have the same nitrogen shift. So I can move it down there. We
And
can
the little shoulder on top, you know what that is?
Future.
That's the NHDs.
Yes.
The isotope.
okay.
Actually, in a nitrogen frozen, the NH2s are suppressed. All you see is the NHD.
I'm going to take a
Yeah.
I remember. The company. No, that's. The company.
let's see. I'm going to wait until your colleague comes back. Then I'm going to quick, like 30 seconds of some RNA stuff, just so you know it exists, and she's also an RNA person. While she's out, let me mention if few things. Once you started project, we actually have a tool for projects, to save projects. So as soon as you start doing stuff that you want to get back to, you should create a project. So if you do save as, you can go to some directory, and I'm going to call it junk because I don't know what's going to end up in here, and I want to remember to delete it. It basically has made a folder that has several folders inside. One of the folders has the data sets. One of the folders has the star file that has the project. There's folders of peak lists, although all the peak list stuff is actually in that star file. That's where everything is. Another thing that will be coming soon that Ellen worked on is every time you save a project, we use the Git source code manager to manage the repository. So every time you save project, it does a Git commit. And we have now a GUI to go back and say, you know, I screwed up starting last Wednesday. I want to go back. So the state of the project as of last Wednesday. You just go select that and it checks out that version. You could branch a project, say I want to why assign you this way or assign you that way. Do things like that. So that's cool. I'm going to say close. Doesn't close that, and then I'm going to say open project. I will just start getting this ready. If I go to test project, see if it works. Yes. So that shows you when you save a project, it knows where every window was, and when you reopen it, you get every window back in theory exactly where it was, and so you can just quit and restart. And I always say when you start working on a project, you should always save the project and quit the software and restart it, because it's good to know that you can actually do this save and restore instead of waiting 3 months down the road and thinking, maybe now I'll save the project and find that something about the project doesn't let it save properly. So I just showed we have projects, which is basically folders on the disk that saves information, including all the windows. So does this look like RNA? It is RNA. And I just, because you guys do RNA, I want to give you a quick whirlwind of some RNA stuff. So under molecules, there's a viewer. And in the viewer, there's a secondary structure viewer. So this is a small fragment of the 5' UTR of the HIV virus. Got a secondary structure there. Another thing we've been working on, just to show you, so the bottom is this dot bracket or Vienna notation. Let's just see if we're silly enough to see if this will work. If I do dot 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 dot. Okay, so now it's just that. So is this going to work, Alan? This is another thing Alan's been working on. I see Simon's working on lots of stuff. We haven't got to Ring yet, so we haven't talked about his stuff. So let's go to secondary structure predict 2D. And cross our fingers because I don't know if this version I have. Oh, look at that. So we've trained, instead of Chat GPT, we've trained RNA GPT. We've made an RNA deep learning language model that's trained to predict secondary structure. It works really well on this one. Yeah. But
let's see, it says peak list. Can you use data?
yes.
To...
Oh, well, there's you can do one thing you can do now that we have a secondary structure. We've spent a lot of time training RNA predictors. So I can go to atom table, and which unfortunately still shows, let me go to RNA. Sure, yeah, there's. If I go to predict predictor, RNA, so our chemical shift predictor will predict if you have a 3D structure of a protein, it'll do a 3-base protein prediction. If RNA, if you have a Vienna dot bracket sequence, it will do a very good, I will say, prediction of what the chemical shifts are, especially things that are in helix and tetraloops and organized structures. You can also do one based on 3-dimensional structure. But if I just click predict, then now these are predictions of the RNA. And then there's several publications published on this. You can go look at. If I go here to atoms and say ribose and base, and if I click on an atom, it tells me something about how it did the prediction. It tells me that they're using this sequence of 5 residues. There are 11 examples in our database, and the mean of that is that we do a combination of a database thing and a machine learning thing if there aren't a lot of values in the database. So I go click on this guy. There's only one in the database, okay? We're actually working, I don't know, somebody may know Sarah Keene at the University of Michigan. She's had a student project where students are actually, we're sending them lists and they work on this, lists of RNAs sequences where there aren't deposited shifts. And then her students make little fragments with those in, and then that data comes back into our database. So we can predict shifts, and then these spectra here are proton, or a nosy, a toxy, and an HMQC, and we can predict what the spectrum would look like, and that's a leg up in doing the assignment. So I go to this peak slider tool here.
You click on the 3 buttons there, you
Oh.
get rid of that.
Oh, thank you.
Hide floating.
Hide floating. Ah, there you go. If I go to actions, restore all peaks. Okay. So now these boxes are where I predicted them. So you can see we actually, for this RNA, we predict things pretty close to where they are. And this little slider tool, if I click on this peak and drag it around, you can see that there are peaks over here in the nosy that are the same atom. So it may be ambiguous where to drag a peak relative to, a box relative to a single peak, but when you see a whole network of peaks moving, you have a lot less ambiguity as to where to go. So just to finish up, this is kind of, so we predicted the 2-me sequence. Now, if we say 2,3D, we come over here, it actually took that secondary structure, and this works for reasonable small fragments, and came up with a 3D structure. Because we have basically a library of structures in helices and tetraloops, and so we have an approximate structure there, and then we can generate constraints from knowing what things are close to each other, and we can then say, anneal that structure, and boom, now we have kind of a reasonable 3D structure. Show constraints. Little green lines are all the little constraints. See what atoms that we think are close in this secondary structure, and you can start adding your own experimental constraints.
Well, this is all theory right now.
This is all theory, exactly. But if you assign a peak, once you actually assign actual peaks, then you put that in as an experiment. I should probably, I know we're over. What I should do is just entertain. I mean, if there's things people want to see, or if we want to move on to other things, or go home.
I could use some troubleshooting on an
Yeah.
SCR file.
Yes, on which file?
I have an SCR file that I can
Oh,
open.
you can't open. Okay, yeah, we'll troubleshoot that. Any other things? I don't know. Anybody on? We haven't heard anything. Can I tell if there are people on Zoom out there? In Zoom.
Yeah. Probably click on your Zoom window that's shown.
Oh, that one.
Oh, there. Yeah.
Click on gallery. like people when they're signed off.
This is, this really,
Or if you open up with the floating meeting controls, they're just.
There we go. yes. Show.
This
Oh,
page
there's 8 participants. Yeah, okay. Well, participants, if there's anything you want to see that we haven't shown, let me know. Otherwise, I'll do a little hands-on stuff. Look at local issues. And let me reiterate, we're not far away, so email us, come by, visit. I know people in Hashim's group, or Hashim and I are always talking about how we need to do a something together, and so that we're gonna have something. Just gotta focus on all things done. Well, let's see what happens.
The good thing I was saying was Bruce being local. There's something you need to do, we can usually get in the ad.
Yes.
As
And
opposed
I'll
to
only
writing
break
your own-
2 or 3 other things.
as opposed to writing your own
Yeah.
software.
We didn't talk about Ring, so I should mention, so Ring is our NMR dynamic stuff. It does lots of RNA, it does CEST, it does CPMG, it does R1 row with examples from some RNA stuff. So, and in theory, it will go, you can process in NMRFX and use the Ring plugin and go pick an NMRFX and then take the intensity of those peaks right into Ring. That's the theory, but we need to have more, people playing with it and finding them. So, yes. Oh, so, are there other, so I don't see like an ACQ US, so that's probably the problem. It can't just have the SCR bucket, it needs to find sweep widths, the spectrometer frequencies and all of that. Which is probably cool.
So they have the entire folder.
Got it. Yep, I bet that's. Yep. I guarantee there's probably, but that is definitely the starting point. The SCR file is just a series of bytes that are the intensities of the FID, but you need to know, you can't even tell how many dimensions there are. Just the SCR file. Yeah.
There's no longer a header sector in the SCR file. There used to be a header sector that
I
stored.
don't think so. I don't think so. Variant files have a header.
But at one point, the certified.
Yeah, I don't think so.
Because I used to read them
Yeah,
without paying any attention to the AC.
yeah, no, I don't, I think they're just. Loading your numbers. And since.
Well, you would know when you're reading an SCR file.
Yeah, I'm just trying to remember, I don't think I skip over anything. The only funny thing I do is that sometimes, I don't know if they still do it, they used to like. Sort of pad values to come out the power of the 2, so you had to worry about that, but otherwise it's just a series. Just a series of intensities. Chat, just want to make sure there's nothing in the chat.
Well, why don't we say formally it's over and I'll thank Bruce.
You're
People
welcome.
who want either online or here want to ask more questions. We'll say formally we're done.
Yep, we're done.
Thank you.
Thank you for coming in persons. Good, yeah, I mean,
Actually, Andy Bird Symposium, Frank Delaglia talk, you mentioned that they're developing more kind of package UE front end.
Yeah.
For NMR type, everybody's converging.
yeah, yes, yes.
You have scripts and you have UEs. NMR pipe used to be purely scripts.
Yeah, they had a sort of a typical TK interface to it for for a fair while. Yeah, Ruby's computers. I saw the guy that used to work on Sparky now at the University of Colorado in Denver that now has Pokey. He's adding processing. So it was kind of a replacement for Sparky for the GUI interface, but now he's going the other way, kind of like I did in that process. So we're gonna have multiple packages that kind of all do the same thing. So I guess that's good.
Yeah, we were working on bugs. Okay, right?
I mean, I'm on the, oh, sorry. I just optimize
Yeah.
the, the 3D structure calculation tool, which called Ponderosa. So
Right.
we just combine Ponderosa and Sparky, so we named the Pokey.
Oh, that's where Pokey came from. Yeah.
So I just worked on optimizing
Yeah,
the
yeah,
parameters
yeah,
for the Ponderosa.
Yeah.
And luckily I got into the also this. But I'm not the developer of all.
We need more NMR users to use the whole pack.
I think this is so really helpful, useful, yeah, especially the prediction.
Yeah,
I like that it does the shifts and it.
Yes.
yeah, the thing we're working on, which I keep putting off and getting distracted. I mean, the slider tool has been really, really useful, the Summers group, et cetera, using it a lot. But you always say, well, if I can sit and slide this peak and look at everything else sliding in place, then the computer ought to be able to slide it for you. So there are some things here which don't really work, but I think they're actually in the GUI already of doing performing these matches. So we're working on some more automated things. But I've always started, it's better to start with the manuals, completely manual, and then get the computer to do more of it. So it still allow you to control and then get the computer to do even more of it. Because when the computer fails, you need to be able to go back and fix things. But if you start with complete automation and it doesn't work, then you're kind of like, well, what do I do? So it kind of worked more bottom up, which isn't as fancy, I guess, it's just outright being completely on. But this is pretty useful, I think. It's were there other. The other thing, you asked about peak list. So I don't know if it'll show if I do the peak list. Yeah, if I choose. Yeah, so this is our simulated peak. We basically have rules that basically say if you're in the secondary structure, you should expect to see these peaks. But you can switch and show an assigned peak, an experimental peak list, and then you'd actually see which connectivities you've actually assigned yourself. But that's basically my rules, and I can't remember what they call it. Blue are intense peaks, and orange are less intense and gray.
So there should be a connection between the GH1 and UH3. We didn't see the carbon. So this is the carbon. Sorry. Sorry.
Okay.
Sorry. This is the carbon.
These are proton connected. Yeah, you do see, for example, these are some.
Yeah.
These peaks are one. I know that the Summers group is like. This is very characteristic peaks from the A across.
Yeah.
To see these long range ones that show up in distinctive areas.
This is the UTR.
Yeah, this is the PBS fragment of the UTR. Primer binding sequence. And it's even truncated from the full.
If you have any, so proton, nitrogen, HSDC, then we can see full connection. Right.
Yeah, good if you can get that data, kind of show that. Right now, I don't do much with nitrogen here. I do, you can see, like when you click here, this is the proton prediction. And if I change this modes to to show carbon predictions. Now, if I click on an atom, now I'm getting the carbon prediction for that atom, right? And you can see there are 0 examples of of a G preceded by a purine and a C and followed by a U and a G in the database, but I do a prediction using sort of support vector regression machine learning.
Why does it show the MNO?
Why does it? Because do I have exchanging? Boom.
Okay.
Some things are driven by who you were, like the summers go off is working on big RNAs and they don't actually, and they're almost always doing deuterated labeling and stuff like that. And they don't often see the MNOs, they're mostly focused on other things. So I don't default to so, and I didn't have good predictions for that. I didn't have good predictions for them, but we've actually got from somebody else that did a lot of predictions.
Which atoms are you showing now?
These are
Proton.
carbon, yeah.
I think nitrogens are on the middle of the.
Yeah, I just don't, I don't show, I don't have a mode for showing predictions for the nitrogens. We predict them, but the data is not great. If you go into, molecule atom table, get rid of like 10 significant digits there, but, you see them down. Yeah, so you can see there are predictions for the nitrogens. They're there. And so if you were to predict an experiment using them, there's prediction.
Now I understand why the voice that this is being.
Yeah.
So we could switch it.
He's trying to.
That's simplified, so we only see inter risk connections. Structure, yeah. One test I like to do, we have this, we can predict a 2D, and then we can convert the 3D, and then we can ask the 3D what its 2D structure was. And
Will it match?
oh, look at that. No, it should have, but it actually, it sometimes, I've got a rule in there for finding certain distances, and actually the rule actually finds a base pair there just because there are 2 protons that are close enough to think, and why that structure I calculated spaced out that U and G, so it could be if I went and refined it a little bit longer and redid that. If we go to this refined structure with complex force field, it actually, this is better to show on a protein, but I have a typical structure calculation with NMR data like this is just a repulsive, keeps atoms apart except when the enemies are pointing near. We have something that's a subset of the amber force field, so you can turn that on and then actually things still doesn't have electrostatics and things that would be really important in RNA. You can find if you calculate a protein structure and then turn on the complex force field, it just kind of shrinks. You'll see it shrink in a little bit because now they're attractive as well as repulsive. I don't know if I did that and then went back here and said from 3D, does it change it now? With that structure, we'll go around a lot more. You normally wouldn't calculate a structure like this in the GUI. There's a command line thing where you can say generate 100 structures and keep the best 20 of them, but this is nice for showing people the principles.
You know that we have a tool called FarBar.
Yeah, sure.
Yes.
Yeah, very familiar.
Yes.
Yeah. This is this little tool we have that I did this 2-3D, not far from by any stretch, but what it does is it'll look at an RNA and it says, okay, from the secondary structure, this is the helix. So the structure calculator, if you're familiar with programs like Cyana or Explore running in torsion angle mode, you're not moving 3D coordinates of atoms, you're just rotating bonds. And so you basically have to have a tree that starts here, goes all the way up and back to here. That makes it hard to sort of predefine components. So what we do is we look at the secondary structure and we say, okay, this connects up here, connects up to here, connects up to here, and this is the end of the helix. So we insert artificial linkers that go over here. And then go back, and now this helix can be predefined. We can just say, set the structure of that as a helix. And now that won't work because you can't, this tree can't have a closed cycle. So we introduce a break here and then put in constraints that pull it back together. And so now we can just sort of predefine the helix, and we can predefine the tetraloop and allow angles where they connect to float. And so we have a little database that has, what are the structures, say, of a bulge. So if you had one bulge there, we've got a little geometry for a bulge, and so we'll predefine the helix before and after the bulge. And then when you go into the refiner, it doesn't change any angles in the helix. It just changes things where the different components come together. So it's not far, but actually for small things, it's very quick. I mean, it'll generate it. Box structure. I don't know what happened. I don't know what happened there. Yeah. I don't know if that's my rules for detecting. I've done this before and I haven't seen it do that. But yeah. A fair amount of online stuff because we're part of, some of this is funded by, we're on the same HIV structure biology questions on CI receptor programming. So yeah, on that grant funds this part of ANMAR FX all on. So, yeah. Anything else anybody wants to see? Then, yeah, no, go play with it. Did I stop the, do I have to do everything to stop the video?
So, the direction will be outside.
Okay,
No,
okay. I'll be careful about what embarrassing things I say that get recorded for posterity.
You can get them to edit it.
Yeah. Yeah. Thanks. Good if there's still Zoom links, there's
There's some people.
a couple out there. Goodbye, everybody. Thanks for watching. And like I say, email us, visit us. We're funded to help.
Thank you so much.
Yeah, you're welcome.
How did you